To find out about the physics involved, we sent Steve back to school. Trinity is the wealthiest and most grand college of Cambridge University and one of the world's leading academic institutions. It's educated prime ministers, princes and spies, but the character we're interested in is the mechanical engineer Dr. Hugh Hunt. He knows gyroscopic forces inside out and, of course, upside down.
Now, I've had an idea, Hugh, and you probably think this is a bit crazy, but I want to drive a car through a real loop-the-loop, a real car. Please tell me that it's possible.
A real car through a loop-the-loop, like a Hot Wheels
Yes.
track. I mean, if I take a firework and shoot it up, well, I can also send a rocket to the moon. That's just a scaled-up version of the same thing. We can just scale up your car for a loop-the-loop, yeah.
It was clear Hugh understood the behaviour of a loop-the-loop better than Steve. Time for a physics lesson.
Steve, the first thing you're going to have to contend with, the biggest thing really, will be the G-forces when you go around this loop. Now, it's interesting to see what happens when you go in a circle. This is just an ordinary tennis ball on the end of a string. Do you reckon I can pick up a house brick with a tennis ball?
No, that's several times its weight.
Right, this is about 10 times, 15 times its weight.
Yeah.
Well, I'm going to do it, just to show you how big these G-forces are. I'll pick up the house brick with the ball, OK?
Oh, wow, that's incredible.
That's not bad, is it?
Tiny tennis ball lifting a great big house brick.
Yeah, absolutely.
And that's just G-forces.
That's just G-forces.
How on earth am I going to steer around the loop while the car's under all this G?
I don't think you have to steer at all.
Really?
Well, I don't think so. Well, let me just think. The track is just going in a loop like this, right? Well, let me just make a little track here. I'll draw a line down the middle. OK, there we go. So let's suppose that was just flat on the ground. Would you have to steer to go along that line?
No, it's a straight line.
It's a straight line, OK. So if I take that straight line and just make a loop out of it, where do you have to turn, left or right? Don't you just follow the line?
But surely the track still goes in one side, moves across to go out the other side. Surely I have to steer across.
That would suggest that there would have to be some kind of kink in the paper like that.
So really, I could just drive in a straight line, straight into the thing and keep the whole thing straight.
Yeah.
That's a real revelation. That's just incredible. So what I'd really like to know now, Hugh, is how fast have I got to enter it if I'm going to get all the way round in one go?
Well, that's a great question. This is all about forces and accelerations, and we're going to use Newton's laws of motion. So let's go down to the lab and we'll do a few sums.
Right, Hugh, as I see it, there are a couple of problems. If I don't get enough speed into the loop and I fall out on my head, that's the worst case scenario.
Yeah,
that's my biggest fear.
Yeah, that's right.
That's, 40 feet potentially onto my head. If I go in too fast, I'm concerned that all these G's you've explained will be outrageous on me and outrageous on this structure. What I want you to help me with is to find exactly the sweet spot, the perfect speed to take it through the loop.
There's a formula for circular motion, and at the top, the speed there has to be 20 miles an hour.
Well, if that's the speed I've got to be at the top to be safe, can we work back to determine what speed I've got to enter the loop at?
There's a formula for that. The 2r plus a half v in squared
Starting to cook my brain a bit now.
equals rg.
Okay.
Here's my final answer. 36
About
miles
36 miles an hour.
Call it 40 miles
Fantastic.
an hour. But you know what we haven't worked out, though?
What's that?
Is what are the G-forces you're going to experience? Because you want to know whether you're going to black out or not. The total G-force you will experience as you enter this loop will be 6G. So imagine you have to carry 5 of you.
That's a lot of G.
It's a lot of G.
And 6 times the weight of the car.
Yeah, the track has to carry, instead of just one car's weight, it's got to carry 6 cars.
I can't tell you how useful this is.
Is your engine designed to cope with 6G? Is your car suspension going to cope with 6 times its own weight? Are your tyres going to cope with having 6 times as much force on them?
It really is a lot to think about. This seemed like a relatively simple stunt when we first looked at it.
What is really nice about all this in my mind is that Newton's laws of motion, this is all just Newton's laws of motion. 350 years ago, Isaac Newton was just coming up with all this stuff, and really things haven't changed since then. So this isn't high tech, this isn't about nanotechnology and microelectronics. This is actually pretty basic, everyday physics and mathematics. And it's not as if this might not be right. This is how it is.
This is how it is.
This is how the world behaves.
Got a huge amount out today, just fantastic. So many more things to think about. It's opened up a lot more potential problems that we can hopefully solve. So that's been very, very useful. Most amazing thing about this is it gives me a bit more confidence because of the science, but at the end of the day, I don't know if that's going to count when I'm staring at the track with my foot in the accelerator.